The closest star system to Earth should be the easiest place to understand, but Alpha Centauri may be one of the biggest blind spots in modern astronomy. James Webb detected something faint, planet-sized, and almost impossible to see. Then it vanished exactly where no one could explain it away. Before we go deeper, like and subscribe, because this may reveal that the universe is hiding its most important secrets right next door. Get ready, we begin. In 2009, James Cameron gave humanity a gift, a world called Pandora, lush and bioluminescent, orbiting a gas giant around Alpha Centauri. A decade later, Lucixian's three-body problem placed an alien civilization there, cold, calculating, and terrifyingly real in the imagination of millions. And in 2016, Stephen Hawking and billionaire Yuri Milner stood in front of cameras and announced Breakthrough Starshot, a plan to fire laser-propelled microprobes toward Alpha Centauri at 20% the speed of light, reaching it within roughly 20 years of travel time. The crowd applauded. The headlines roared. Humanity, it seemed, had already decided what Alpha Centauri was our destination. 4.3 light-years. That is the number burned into the cultural memory of anyone who has ever looked up at the night sky in the southern hemisphere and spotted the third brightest star visible to the naked eye. So close by cosmic standards that it feels almost neighborly, so familiar. After decades of science fiction and serious scientific proposals, that most people assume we know it the way we know our own backyard. That assumption is the problem. Because as of 2024, after all the films, all the novels, all the billion-dollar telescope programs, all the peer-reviewed papers, astronomers had not confirmed a single planet orbiting Alpha Centauri A or Alpha Centauri B. Not one. 0 confirmed worlds around the two sun-like stars that anchor the system we have been romanticizing for half a century. Let that sit for a moment. We know more about the surface geology of Pluto, a frozen rock sitting 3 billion miles from Earth, so far away that sunlight reaching it is dimmer than a street lamp on a foggy night. Than we know about whether any planet at all orbits the star system. Right next door, NASA's New Horizons spacecraft flew past the Pluto in 2015 and sent back images detailed enough to map its nitrogen ice plains, its mountain ranges of water ice rising nearly 10,000 feet, the reddish patchwork of its surface chemistry. Pluto, the thing we demoted from planet status and largely stopped caring about. We have better maps of that than of the nearest stellar neighborhood. This is not a minor gap in knowledge. It is a chasm dressed up as familiarity. Alpha Centauri is not one star. It never was. The system contains 3 Alpha Centauri A, a star about 10% more massive than the Sun and roughly 22% wider, burning slightly hotter and more luminously. Alpha Centauri B, smaller and cooler than the Sun, an orangish star that would be considered pleasant and stable on its own. And Proxima Centauri, a red dwarf orbiting the other two at a staggering distance, probably somewhere between 4,300 and 13,000 astronomical units away, meaning it takes Proxima somewhere between 500,000 and 2 million years to complete one orbit around its companions. Proxima is actually the closest individual star to Earth, a title it holds purely by proximity and not by any connection meaningful to human storytelling. Alpha Centauri A and B are gravitationally bound to each other, locked in a mutual orbit that takes 79.9 years to complete. At their closest approach, they are separated by 11 astronomical units, roughly the distance from the Sun to Saturn. At their farthest, that gap stretches to 36 astronomical units, well past the orbit of Neptune in our own system. 2 stars, circling each other, their gravitational influence constantly reaching, pulling, reshaping anything that might dare to orbit either one of them. And here is where the idea of familiarity begins to crack. You are probably thinking, We have the Hubble Space Telescope. We have the James Webb Space Telescope. We have ground-based observatories on every inhabited continent. We have thousands of astronomers working on exoplanet research full-time. How could we possibly not know what is orbiting the closest star system to Earth? That question feels reasonable. It feels like the kind of thing that should have a simple answer, like an oversight that could be corrected with a slightly better camera or a longer observation window. That is exactly what I need you to understand, because the answer is not simple, and the correction is not easy. And the reasons behind both will change the way you think about every claim ever made about planets around distant stars. Trying to find a planet next to Alpha Centauri A is like trying to read a newspaper while someone holds a spotlight directly in your face. The star is so bright, so overwhelming in the field of view of any instrument pointed its way, that its light floods every detector, saturates every pixel, and drowns out the comparatively whisper-quiet signal of anything orbiting nearby. Proximity, in this case, is not an advantage. It is a wall made of photons. The gravitational complexity makes things worse. When two stars orbit each other as A and B, do they exert forces on any potential planets that are orders of magnitude larger than the gravitational tug a planet would exert back? The primary method astronomers use to detect exoplanets around single stars is called the radial velocity method. Measure the tiny wobble a planet induces in its host star as it orbits, detected as a Doppler shift in the star's light. This works beautifully for single stars with patient observation. Around Alpha Centauri, the gravitational conversation between A and B completely overpowers that signal. It is the astronomical equivalent of trying to hear a whisper during a thunderstorm. We built a plan to send a spacecraft there before we confirmed there was anything to visit. That is roughly equivalent to booking a flight, packing your bags, and heading to the airport for a destination that has never appeared on any map. Breakthrough Starshot, for all its genuine scientific ambition and its remarkable engineering proposals, was announced when the question of whether Alpha Centauri A or B even hosts planets remained entirely open. The spacecraft would be postage stamp-sized. The laser array would need to be kilometers wide. And the target was a system whose planetary architecture we could not describe with any certainty. To be clear, the ambition is not the problem. The problem is what the ambition revealed that humanity had so thoroughly convinced itself of Alpha Centauri's familiarity that it began planning the journey before completing the map. 4.3 light years, the nearest star system, and until 2024, almost completely hidden from us by the very brightness and complexity that makes it feel so close. But that blindness didn't come from laziness. It came from a physical paradox that not even Einstein could have rescued us from. Confirmation bias does not announce itself. It does not walk through the door wearing a sign. It works quietly, through the accumulated weight of reasonable-sounding assumptions, each one building on the last until the entire structure feels too solid to question. In astronomy, it works like this: a star is close, so we study it often. We study it often, so we write about it. We write about it, so it enters the cultural vocabulary. It enters the cultural vocabulary, so filmmakers use it. Novelists imagine it. Scientists name proposals after it. And somewhere in that loop, somewhere between the observatory and the box office, we stop asking whether the premise is actually confirmed and start treating it as settled. Alpha Centauri A is 1.1 times the mass of the Sun. Its surface temperature sits just a few hundred degrees Kelvin above the Sun's. Its age is estimated at roughly 5 to 6 billion years, comfortably within the range where complex chemistry and conceivably life has had time to develop on any planets that might orbit it. Alpha Centauri B is smaller, cooler, but still a stable, long-lived star, on paper. The system checks every box that the search for habitable worlds has traditionally prioritized: sun-like stars, mature age, stable energy output, positioned close enough that any signal would be detectable in principle. So the scientific community, and then the broader culture, and then the filmmakers, and then the billionaires looked at those characteristics and made a decision, not explicitly. Nobody held a meeting and voted, but collectively, gradually, the assumption crystallized Alpha Centauri must have something worth visiting. The problem is that assumption ran about 20 years ahead of the evidence. Breakthrough Starshot was announced in April 2016 at the One World Observatory in New York. Stephen Hawking stood beside Yuri Milner and Mark Zuckerberg, and the proposal was extraordinary in its ambition: use a ground-based laser array of enormous scale to accelerate gram-weight spacecraft, literally smaller than a postage stamp, equipped with a light sail to 20% of the speed of light. At that velocity, the probes would reach Alpha Centauri in roughly 20 years of travel time, beam back data across 4.3 light years, and give humanity its first close look at another star system. The engineering challenges were staggering. The cost projections were in the billions, and the target Alpha Centauri was selected precisely because of its proximity and its sun-like character. At the time of that announcement, no planet had been confirmed around Alpha Centauri A or B, none. The destination was chosen on the basis of stellar type and distance alone, not on any confirmed planetary architecture. The equivalent would be launching a Mars rover, based solely on the fact that Mars is red and nearby, without any orbital data, any surface mapping, any atmospheric measurements. Except in this case, the journey would take 2 decades and the spacecraft would be the size of a chip. Again, the ambition is not the point. The engineering thinking behind Starshot is genuinely innovative, and proximity to Earth is a perfectly rational reason to prioritize a target. But the episode reveals something deeper, a collective cognitive commitment to Alpha Centauri as a destination that existed independently of the evidence. We had decided, and once a civilization decides, the machinery of culture makes that decision very hard to revisit. Now here is where the story gets more complicated and more instructive. In 2016, the same year as the Starshot announcement, astronomers confirmed a planet orbiting Proxima Centauri, Proxima AB, as it was designated, sits within Proxima's habitable zone, receives roughly the right amount of energy for liquid water to potentially exist on its surface, and has a minimum mass of about 1.27 times that of Earth. On those numbers alone, it sounds promising. The headlines were enormous. Then came the fine print. Proxima Centauri is a red dwarf, a small, dim, extraordinarily volatile star that periodically erupts in X-ray flares of savage intensity. These are not the gentle solar flares the Sun occasionally produces. Proxima's flares are proportionally far more energetic relative to the star's total output, and they bombard the surface of Proxima b with radiation that would strip away an unshielded atmosphere over geological timescales. Because Proxima b orbits so close to its dim host star, completing one orbit in only 11.2 days, it is almost certainly tidally locked, meaning one side permanently faces the star in scorching heat, while the other faces permanent darkness. The habitability window, once thought wide, is now considered by most researchers to be vanishingly narrow at best. So the one confirmed planet in the Alpha Centauri system is probably uninhabitable, and the 2 stars most likely to host something worth visiting, A and B, the sun-like ones, the ones we built the cultural mythology around, remain, as of 2024, without a single confirmed companion world. The quiet star is screaming. The accessible one is mute. Finding a planet around a binary star system is a categorically different problem than finding one around a single star, and the gap between those 2 situations is not a matter of degree. Imagine you are standing outside a building at night, trying to detect a single candle flame burning somewhere inside. The building has one window, and through it, you can see a small glow. Difficult, but possible with patience and the right instruments. Now imagine that same building. But instead of one candle, there is an enormous bonfire in the center of the room dancing, shifting, constantly changing the pattern of light and shadow across every surface. Your candle is still there, somewhere, but every measurement you take is contaminated by the bonfire's movement. Every tool you use picks up its fluctuations. The candle is not gone. You simply cannot separate it from the noise. That is what a binary star does to every detection method currently in use. The radial velocity method, which measures Doppler, shifts in starlight, caused by a planet's gravitational tug, sees the far larger gravitational conversation between A and B and cannot cleanly extract a planetary signal from it. The transit method, which looks for a periodic dimming when a planet crosses in front of its star, requires long, uninterrupted observation windows that the binary's orbital complexity makes extremely difficult to obtain cleanly. Direct imaging requires blocking the star's light entirely. But when two bright stars are involved, the scattered light from both creates a contaminated field that defeats most coronagraphic systems. Two stars, constantly moving around each other over a 79.9-year period, constantly reshaping their mutual gravitational field, constantly flooding every instrument pointed their way with compounded, overlapping stellar noise. If we are wrong about what orbits the nearest star system, a system we have observed continuously for decades, a system bright enough to study with amateur telescopes, a system that has been the subject of more dedicated scientific attention than almost any other, then the question becomes unavoidable. If we are wrong about the closest star, how many others are we wrong about? And this is where physics begins to turn against itself, because proximity, the very thing that should have made this easier, is exactly what broke everything. Common sense says closer is clearer. You see the moon in sharp detail craters, Mare plains, the rough texture of its highlands, while Mars, even at its closest approach, is just a reddish smear without a telescope. Mars is closer than Jupiter, so you see more of it. Jupiter's closer than Neptune, so its bands and moons are visible, while Neptune is little more than a pale blue dot. The rule seems airtight. Shrink the distance, sharpen the image. Every child learns it. Every early astronomer assumed it. And in the ordinary world, in every situation that does not involve detecting faint objects next to blindingly bright ones, it is completely true. In the search for exoplanets, the rule quietly reverses itself. Not always, not in every method, but in the specific problem of finding planets around the nearest stars through direct observation. Proximity becomes a liability so severe it can render a target effectively unobservable. Stars hundreds of light years away, dim, distant. Their light arriving as a faint and manageable stream are, in many cases, far easier to analyze for planetary companions than a star sitting 4.3 light years from Earth, pouring so much light into any instrument pointed at it that the detectors simply cannot cope. Alpha Centauri A has an apparent magnitude of roughly negative 0.01. To put that in context on the scale astronomers use for brightness, lower numbers mean brighter objects, and negative numbers mean extraordinarily bright ones. The full moon sits around negative 12.7. Venus at its peak reaches negative 4.9. Alpha Centauri A, to the naked eye, blends with Alpha Centauri B into a single point of light that ranks as the third brightest star in the night sky. Pointed at this with James Webb's mid-infrared detectors instruments of extraordinary sensitivity, designed to pick up the faint thermal glow of objects billions of light years away, the result would not be a clear image. The detectors would saturate, the sensors would flood, the signal would not be too faint to read. It would be so overwhelming that it would erase everything around it. The way a truck's high-beam headlights pointed directly into a camera lens at close range do not produce a photograph of the truck. They produce a white rectangle of pure sensor overload. With the Firefly, you were trying to photograph somewhere invisible inside it. That Firefly analogy is not casual. A planet the size of Saturn orbiting Alpha Centauri A at a distance of 2 astronomical units. The rough distance at which such a planet might plausibly exist would be approximately 10,000 times fainter than the star itself when viewed in mid-infrared wavelengths. 10,000 times. The star's light does not just outcompete the planet's signal, it buries it under an avalanche. Which is why astronomers spent decades leaning heavily on the radial velocity method, the technique that does not require imaging at all, and therefore does not require looking at the star directly. The logic of radial velocity is elegant and intuitive. When a planet orbits a star, the planet's gravity pulls on the star in return, causing the star to wobble slightly around the shared center of mass between them. That wobble is tiny, imperceptible to the eye, but it produces a measurable Doppler shift in the star's light. As the star moves fractionally toward Earth in its wobble, its light compresses slightly toward the blue end of the spectrum. As it moves away, the light stretches toward the red. Measure those shifts precisely enough, consistently enough, and you can infer the presence of a planet without ever seeing it directly. Think of watching a figure skater performing a slow spin while holding something in one outstretched hand. You cannot see what they are holding. It is too small, but you can watch the subtle, rhythmic offset in their rotation and deduce that something with mass is out there, pulling their center of gravity slightly off axis. That is radial velocity. Patient, indirect, and when applied to single star systems, remarkably powerful. Jupiter exerts enough gravitational pull on the Sun to make it wobble at roughly 12.5 meters per second. That is a detectable signal. It took years of careful observation to measure it cleanly, but it is there, consistent or real. The method works. Alpha Centauri A and B pull on each other at velocities on the order of several kilometers per second, thousands of times larger than any planetary signal could ever produce. The two stars are not a quiet background against which a planet's tug can be isolated. They are a gravitational storm, each one yanking the other back and forth across a 79.9-year orbit. Their mutual influence so dominant that it completely swamps the signal of any planet that might be tagging along for the ride. Any algorithm trying to strip out the binary's contribution to find what is left faces a mathematical problem of extraordinary difficulty. Subtract too little, and the binary's motion masquerades as a planet. Subtract too much, and you erase the planetary signal entirely. The margin for error is razor thin, and as the field would discover in 2012, razor-thin margins have a way of cutting the wrong direction. There is a particular flavor of irony in all of this that the universe seems to have engineered with some care. Astronomers spent decades building instruments of increasing power, larger mirrors, more sensitive detectors, faster computers for processing the data, and each advance made it possible to find planets around stars that were more and more challenging to observe. Hundreds of light years away, thousands of light years, in the Milky Way's far reaches, the catalog of confirmed exoplanets grew into the thousands, with worlds found around dim red dwarfs, around metal-poor ancient stars, around stars in dense stellar clusters. And through all of that, the nearest star system sat stubbornly unresolved, too bright to image directly, too dynamically complex for radial velocity to untangle, a monument to the universe's sense of humor about human ambition. The closer you get, the worse it works. The nearer the neighbor, the higher the wall. When the light of the nearest star becomes a barrier, do we build a ladder, or do we find a way to bring the wall down? Astronomers chose, eventually, to bring the wall down, not with a sledgehammer, but with something far more unusual: a blindfold, a calculator, and a coronagraph. But that story belongs to what came next. What came first was a failure so spectacular, so publicly humiliating, and so scientifically instructive that it reshaped the entire way the field approaches Alpha Centauri, and arguably, the way it approaches any planetary claim made in difficult observational conditions. This frustration once led to one of the most painful false alarms in the history of modern astronomy. In October 2012, a team of astronomers led by Xavier Dumusc, working with data from the European Southern Observatory's HARPS spectrograph at the La Silla Observatory in Chile, published a paper in the journal Nature announcing the detection of a planet orbiting Alpha Centauri b. The planet was designated Alpha Centauri bb. Its minimum mass was estimated at 1.13 times the mass of Earth, practically identical to our own world. It orbited Alpha Centauri b with a period of 3.2 days, placing it far inside any habitable zone. Its surface almost certainly scorched to temperatures exceeding 1,200 degrees Celsius. Nobody claimed it was a second Earth in any meaningful habitability sense. But the announcement carried something more important than habitability. It carried proof of concept. If a rocky, Earth-mass planet could exist in the Alpha Centauri system at all, the gravitational architecture of the system was not hostile to planet formation. And where there was one rocky planet, even a scorched one, there might be others cooler, more distant, more interesting. The press did not report it as proof of concept. They reported it as the discovery of an Earth next door. Headlines across every major outlet competed for the most dramatic framing. The scientific community was more measured in public, but privately, the excitement was real. For decades, Alpha Centauri had been the destination of imagination. Now it was threatening to become the destination of fact. 3 years later, the fact evaporated. In 2015, a team led by Artie Hatzis published a reanalysis of the same HARPS dataset and reached a deeply uncomfortable conclusion. The signal attributed to Alpha Centauri b was not a planet. It was a statistical artifact, a ghost produced by the specific way the research team had processed and filtered the radial velocity data from a binary star system. The signal was real in the mathematical sense that it appeared in the numbers, but it was not real in the physical sense of corresponding to an orbiting body. It had been created inadvertently by the analysis itself. Understanding why this happened requires sitting with the complexity of what radial velocity data looks like when collected from a binary system over years of observation. Imagine attending a symphony orchestra performance, a full ensemble, strings and brass and percussion, all playing simultaneously, and being asked to transcribe only the sound of a single triangle player seated somewhere in the third row. The triangle player is real. They are producing sound, but the sound of the full orchestra surrounds and penetrates every recording you make, and separating the triangle's contribution from the wall of violin and cello and French horn requires assumptions, mathematical assumptions. You build an algorithm that models the orchestra's expected sound and subtracts it from the recording, leaving in theory just the triangle. But if your model of the orchestra is even slightly wrong, the subtraction leaves artifacts, patterns in the residual noise that were never produced by the triangle at all, but that your algorithm inadvertently sculpted from the collective sound of 100 other instruments. That is what happened with Alpha Centauri b, the binary's gravitational interaction. The constant mutual pull of two stars over a 79.9-year orbital dance produces a complex, time-varying signal in the radial velocity data. To find a planetary signal inside that data, you must first model and subtract the binary's contribution. The model Dumusc's team used was sophisticated, peer-reviewed, and entirely reasonable by the standards of 2012. It was also, as it turned out, imperfect in ways that produced a residual signal at a period of 3.2 days. A period that matched nothing real, but matched the noise architecture left behind after an imperfect subtraction. The brain, when shown a complex pattern, will find structure in it. That is not a flaw. It is the engine of science. But it is also the engine of certain categories of error. You think you hear the whisper, but the whisper is the orchestra, rearranged. After 2015, the field changed, not in a dramatic, announced way. There was no press conference declaring a new era of caution, but in the accumulation of individual decisions made by reviewers, editors, and research teams when anything involving Alpha Centauri crossed their desks. The bar for acclaim about this system rose sharply. Multiple independent data sets, multiple detection methods, multiple institutions, a single spectroscopic signal, however clean it appeared, would no longer be enough. The lesson of Alpha Centauri BBEs had been absorbed into the epistemic culture of the field. That heightened standard was still in place in 2024 when a different team, using a completely different instrument, a different wavelength range, and a different detection method, found something in the data that did not fit neatly into any category. Not clearly a planet, not clearly noise, and not clearly gone. You are already asking it if 2012 turned out to be wrong. Why should 2024 be any different? That is exactly the right question to sit with. After a decade of failure and skepticism, astronomers decided to stop observing the conventional way and do something that had never been attempted before. The James Webb Space Telescope, launched on December 25, 2021, folded inside an Ariane 5 rocket like an origami crane waiting to unfurl. Its primary mirror spans 6.5 meters across, assembled from 18 hexagonal, gold-coated beryllium segments that deployed in sequence over the weeks following launch. It operates at negative 233 degrees Celsius, colder than most of the vacuum of deep space, because the infrared signals it hunts are so faint that even the thermal noise of a slightly warmer instrument would drown them out. Webb was built to see the first galaxies that formed after the Big Bang, more than 13 billion years ago. It peers through dense clouds of interstellar dust that are opaque to ordinary light, reading the infrared glow of stellar nurseries, protoplanetary disks, and the atmospheric chemistry of distant worlds. By any reasonable measure, it should be able to handle anything the universe places in front of it. Alpha Centauri A has an apparent magnitude of approximately negative 0.01. That number, for anyone unfamiliar with the astronomer's inverted brightness scale, places it among the most overwhelmingly luminous objects in the night sky, not because it is an unusually powerful star, but because it is so extraordinarily close. Webb's guide star system, the set of sensors that lock onto reference stars to hold the telescope's orientation steady with extraordinary precision during long exposures, was specifically engineered to avoid stars brighter than a certain threshold. Look directly at something too bright, and the fine guidance sensors saturate. The signal stops being information and becomes noise. The telescope loses its lock, the observation fails, and in the worst case, the bright source damages the detector's calibration for subsequent observations. The most powerful space telescope ever constructed cannot look directly at the nearest star system. Let that land for a moment. It is a perfect paradox, and it is entirely real. The instrument that brought us images of galaxies from the edge of observable time, that resolved the atmospheric spectrum of exoplanets hundreds of light years away, that photographed protoplanetary disks forming around infant stars. This instrument would have its sensors flooded and its guidance systems destabilized if anyone simply pointed it at Alpha Centauri A and pressed the equivalent of a shutter button. The solution could not be brute force. It had to be something more oblique, literally. The technique the team devised is called a blind offset, and it is as counterintuitive as its name implies. Rather than attempting to point Webb at Alpha Centauri A directly, which would trigger the saturation problem immediately, the engineers and astronomers first locked the telescope onto a completely different star Epsilon Muscae, a star in the constellation Musca, significantly dimmer, and well within Webb's safe operating range for guide star acquisition. With Epsilon Muscae locked in and the telescope's orientation stabilized, the team then commanded Webb to execute a precisely calculated slew, a rotation of the entire telescope by an angle determined not by looking at the destination, but by computing it mathematically from the known positions of both stars in the celestial coordinate system. The target of that slew was the coronagraph at the heart of Webb's MIRI instrument, the mid-infrared instrument, which operates across wavelengths from 5 to 28 micrometers. At the focal plane of MIRI sits a coronagraph, a small opaque disk positioned precisely at the point where the image of the target star forms, physically blocking that starlight before it can spread across the detector. The coronagraph is not a filter. It does not dim the star uniformly. It eliminates the star's direct contribution at the center of the field, while allowing the surrounding region, the space where planets would orbit, to remain visible. The concept dates back to solar coronagraphs used to study the sun's corona by blocking the solar disk. But in the context of exoplanet hunting, it has become one of the most powerful tools in direct imaging astronomy. Getting Alpha Centauri A's image to fall onto the center of MIRI's coronagraph without looking at Alpha Centauri A required the angular precision of the slew from Epsilon Muscae A to be accurate to within thousandths of an arcsecond. An arcsecond is 1/3600th of a degree. A thousandth of an arcsecond is 1/3,600,000,000th of a degree. The engineers had to rotate a telescope the size of a tennis court, positioned 1,500,000 kilometers from Earth at the second Lagrange point, by an angle so small it would be invisible to any measuring instrument available to ordinary human experience, and land the image of a star. They were explicitly not looking at onto a disk roughly the width of a human hair at the focal plane. Blindfolded, 100 steps, finger extended, candle blocked without ever opening your eyes. If that sounds improbable, it is because it is. The technique had never been successfully applied to a target as bright or as demanding as Alpha Centauri A before. It required months of planning, precise astrometric data about both stars' positions, careful modeling of the telescope's pointing behavior, and multiple rounds of engineering review. The margin for error was essentially zero too far off-center, and the coronagraph would not block Alpha Centauri A's light adequately, flooding the MIRI detector too far the other way, and the target region would fall outside the useful field of view entirely. Once the coronagraph does its work, the suppression is dramatic, but not total. Alpha Centauri A's brightness, reduced by a factor of roughly 1 billion in direct starlight terms through a combination of the coronagraph and the instrument's optical design, comes down to something in the range of a factor of several thousand in the scattered light residual that remains around the occulted star. Still bright, still a formidable background against which anything faint must be detected, but no longer an avalanche, more like a very bright room than a searchlight pointed at your face, difficult, but navigable with the right processing. If we have to blindfold the most powerful telescope in history just to look at the nearest star, what does that tell us about where the actual ceiling of our technology sits? The answer, it turns out, is not the ceiling we assumed. Because beyond the blindfold, beyond the coronagraph, beyond the months of engineering preparation, the data still had to be interpreted. An interpretation, as 2012 had already demonstrated with brutal clarity, is where certainty goes to negotiate. And then, as layers of light were peeled back one by one, something emerged from the dark. Kevin Wagner is an astronomer at the Steward Observatory, University of Arizona. In August 2024, his team successfully executed the blind offset maneuver for the first time in Webb's operational history, placing Alpha Centauri A behind MIRI's coronagraph and collecting the first mid-infrared observations of the region surrounding the nearest sun-like star ever obtained from space. The raw data came back as it always does from Webb compressed, calibrated at the instrument level, and at first glance utterly inscrutable to anyone without both the software and the years of experience needed to read what the numbers actually mean. What followed was not a moment of revelation. It was weeks of pipeline processing, each step designed to strip away a different category of contamination from the signal. The first layer removed was the coronagraph's own scattered light signature. Even with Alpha Centauri A sitting behind the occulting disk, the star's light diffracts around the edges of the mask, creating a predictable but complex pattern of residual brightness across the detector. This pattern is modeled using reference observations other stars of known brightness observed through the same coronagraph under similar conditions and subtracted from the science data. One of those reference stars was Epsilon Muscae, the same star used to acquire the blind offset pointing in the first place, repurposed now as a photometric and coronagraphic calibration source. The second layer addressed thermal noise. Miri operates at 6 degrees Kelvin, but even at that temperature, the detector accumulates a slow background of thermal electrons that mimic faint sources if not corrected. The pipeline applies dark frames, background frames, and flat field corrections to separate instrumental artifacts from real astrophysical signal. The third layer involved normalizing the entire data set to a consistent flux scale, accounting for the slight pointing jitter that accumulates over the course of a long exposure, even with Webb's extraordinary stability, and flagging any cosmic ray hits individual high-energy particles that slam into the detector during the observation and produce sharp, bright spikes that could easily be mistaken for point sources if not identified and removed. Think of what you are left with after all of that as a piece of paper that was dipped in water, dried unevenly across a wrinkled surface, and then had a corner splashed with coffee at some point during the process. Somewhere on that paper, someone made a faint pencil mark before the water hit it. Your job is to find the pencil mark and confirm it was made by a pencil, not by the water stain, not by the coffee, not by the pressure wrinkles in the paper. Every processing step makes a decision about what is stain and what is signal. And every one of those decisions rests on assumptions. Assume the wrong model for the water stain, and you either reveal a mark that was never there, or you erase one that was. The team knew this. They had lived through 2012, or at minimum, had studied it carefully enough to treat it as a founding cautionary document. Every processing choice was made conservatively, with multiple independent pipelines run in parallel to check whether different methodological assumptions produced the same result in the residual data. The timing of the August 2024 observation was not accidental. Alpha Centauri A and B orbit each other with a period of 79.9 years, and their separation on the sky, as seen from Earth, changes continuously across that orbit. In 2024, the two stars were positioned at an angular separation that placed Alpha Centauri B far enough from Alpha Centauri A's coronagraphic field that its own scattered light contribution to the MIRI data was significantly reduced compared to what it would be when the stars are closer together in their apparent positions. The window was narrow, the geometry was favorable, and the blind offset had worked for the first time. Alpha Centauri A was sitting behind Miri's coronagraph. The scattered light was at a manageable level, and the detector was reading the surrounding sky with a sensitivity that had never before been achieved for this target. What emerged in the processed data was a point source, a single, faint, localized concentration of mid-infrared flux brighter than the surrounding background by a statistically significant margin, compact in a way that matched the expected point spread function of a real astrophysical object rather than an extended artifact, positioned at an angular separation from Alpha Centauri A, corresponding to approximately 2 astronomical units in physical distance. It was roughly 10,000 times fainter than the host star. That ratio is large enough to make detection extraordinarily challenging, but within the range that MIRI's coronagraphic performance was expected to achieve under optimal conditions. This was, by every measure available at the moment of its detection, the most credible candidate signal ever recorded from the vicinity of Alpha Centauri A. Not the most certain credible, and certain are very different words in this field, and 2012 made sure of that. But the most credible, the most technically grounded, the most difficult to dismiss as simple instrumental noise. $3 billion, 10 years of construction, hundreds of scientists across a dozen countries, all of it converging on a single point of light 10,000 times dimmer than the star beside it, and you expect a clean answer. It was not clean. It was faint, uncertain, and entirely possible that it was an illusion, but it sat in exactly the place no one had dared to dream. The habitable zone of Alpha Centauri A sits between approximately 1.2 and 1.4 astronomical units from the star, the orbital band, where temperatures are moderate enough for liquid water to exist on the surface of a rocky planet. Assuming that planet has an atmosphere of reasonable composition, in that respect, it mirrors our own sun's habitable zone with eerie precision, which begins just inside Earth's orbit at roughly 0.95 astronomical units and extends to about 1.7. Alpha Centauri A burns slightly hotter and more luminously than the sun, so its habitable zone is pushed outward a little, but the principle is the same. The range is comparable, and the physics is identical. Nobody expected Webb to find a rocky world there. That was never on the table. Earth-sized planets in a habitable zone, even around a nearby star, remain below the detection threshold of any instrument currently in operation. What the team was cautiously hoping for, and even this felt like a long shot, was a signal consistent with a giant planet, something the size of Saturn, or perhaps Jupiter, a gas world large enough and warm enough from its own internal heat to radiate detectably in mid-infrared wavelengths, positioned far enough from Alpha Centauri A that the coronagraph could separate its signal from the star's residual scattered light. A gas giant at 2 astronomical units would sit at the outer edge of the habitable zone, far too warm and massive to be a direct candidate for surface life. But a gas giant in that position could host moons, large moons with rocky surfaces, subsurface oceans, geothermal activity. Europa, orbiting Jupiter at 5.2 astronomical units from the Sun, maintains a liquid water ocean beneath its ice shell through tidal heating alone. Enceladus, orbiting Saturn, actively vents water vapor into space from geysers at its south pole. The presence of a gas giant at 2 astronomical units from Alpha Centauri A would not be a detection of life, but it would be something in architecture, a structure, a sign that the system is more complex than an empty field of gravitational chaos. After the data processing was complete, after the scattered light model had been subtracted, after the thermal noise corrections and the cosmic ray removals, and the cross-pipeline validation checks, a point source remained: one localized concentration of mid-infrared flux, compact, statistically significant, sitting at an angular separation from Alpha Centauri A that translated to approximately 2 astronomical units in physical distance. Its brightness ratio relative to the host star, roughly 10,000 to 1. Its spectral character in the mid-infrared, consistent with the thermal emission of a warm body, not reflected starlight, which would have a different spectral shape, but intrinsic heat radiation from an object that has retained warmth from its formation, or from tidal and radiogenic processes, its estimated mass, based on luminosity models for self-luminous planets at this age and orbital distance, somewhere between 0.3 and 1 times the mass of Jupiter. In other words, Saturn class to Jupiter class. The team designated it S1, 2 astronomical units, right at the outer edge of the habitable zone, exactly the kind of object that, if confirmed, would rewrite the story of Alpha Centauri from an empty neighborhood into a structured planetary system with moons that might harbor conditions for liquid water. The signal was not shouting. It was a whisper in processed data, statistically real, but demanding verification before anyone could call it a discovery. The initial paper went to Archiv, the preprint server where astronomers share results before formal peer review, with language calibrated to the post-2012 era. Candidate signal. Requires confirmation. Consistent with a planetary companion, but not yet confirmed as such. Every phrase chosen to be accurate rather than exciting, because the field had learned what excitement without verification costs. The word planet appeared in the paper, but always hedged, always conditional, always surrounded by qualifiers that made the epistemological status explicit. Privately, the conversation was different. Among the people who had worked on the data, who understood what it had taken to get even a single credible observation of this region of sky, who knew how many previous attempts had ended in noise or retraction. The reaction was not cautious at all. This was the strongest, most technically grounded signal anyone had ever pulled from the vicinity of Alpha Centauri A. Not conclusive, but the most credible thing the field had produced from that target in its entire history. 10,000 times fainter than the star. Correct position, correct temperature, correct size range. What would you call it if not a planet? The universe answered that question in February 2025. The answer was nothing. S1 was gone. The universe, as always, had no interest in being predicted. Not an instrument illusion, not a calculation error. The signal vanished, and that disappearance contained information more disturbing than the signal itself. Webb's follow-up observation of Alpha Centauri A was scheduled for February 2025, a confirmation epoch designed precisely to test whether S1 would appear at the same position with consistent brightness. Confirmation observations are the mechanism by which candidate signals become detections and detections become discoveries. The logic is simple. A real planet in a stable orbit will be there when you look again. Its position will have shifted predictably, consistent with orbital motion. Its brightness in mid-infrared will be comparable. The data will converge into a coherent picture of something moving through space on a calculable path. S1s was not there, not fainter, not shifted to a slightly different position consistent with orbital motion, not partially obscured by some new source of noise in the data. The coordinate where it had appeared in August 2024 showed nothing above background level. The signal that had defined the most promising Alpha Centauri observation in history had vanished as completely as if it had never existed. A third observation was conducted in April 2025. The result was identical, empty, background noise, coronagraphs scattered light, and nothing else. Before any interpretation was possible, the team had to rule out the mundane explanations. The first check was instrumental had something changed about Webb's performance, about the MIRI detector, about the coronagraph's alignment. That might have affected sensitivity. The answer was no. Webb's other observations from the same period showed no degradation. The instrument was functioning within normal parameters. The coronagraph was performing as expected. If S1 had been a persistent point source at that location, the February and April observations would have detected it. The second check was noise variability. Could the August 2024 signal have been an unusually bright fluctuation in the background noise, a statistical outlier that the pipeline had misidentified as a real source? The team examined the noise properties of the background across all three observation epochs and found them stable and consistent. The noise floor had not changed. A signal of S1's significance in August simply should not have appeared by chance. The statistical weight of the original detection was not that of a marginal fluctuation. Three hypotheses survived initial scrutiny. The first S1 was an image artifact produced by the coronagraph itself. Some specific interaction between Alpha Centauri A's scattered light and the coronagraph optics that generated a spurious point source in August, but not in the other two epochs. The problem with this hypothesis is structural coronagraphic artifacts are determined by the geometry of the optical system and the position of the star behind the occulting disk. If the telescope pointing and the stellar flux were consistent across all three observations, and they were the artifact pattern should have been consistent too. The morphology of S1 in August also did not match the known artifact patterns for Miri's coronagraph at that angular separation. The artifact hypothesis could not be cleanly dismissed, but it could not explain the data without invoking behavior the instrument had never shown before. The second S1 was a background object, a distant star or galaxy, that happened to be positioned near Alpha Centauri A in the August observation, whose light was detected by Miri and mistaken for something associated with the Alpha Centauri system. The problem here is astrometric. Alpha Centauri A moves across the sky at a measurable rate. Its proper motion is substantial precisely because it is so close to Earth. Between August 2024 and February 2025, the star and everything gravitationally bound to it would have shifted position relative to background objects. If S1 were a background object, it should have appeared to move relative to Alpha Centauri A in the February observation, shifted to a slightly different position because Alpha Centauri had moved while the background stayed fixed. No such shift was observed. The background object hypothesis requires either that the proper motion calculation was wrong, or that S1 was not cataloged in any existing stellar or galactic survey at that position, and both of those are difficult to sustain against the evidence. What remained the hypothesis that could not be ruled out by any of the available data was that S1 is a real planet, and that its orbit had carried it out of the region accessible to Miri's coronagraph between the August 2024 observation and the February 2025 follow-up. Miri's coronagraph does not provide a complete view of the space surrounding Alpha Centauri A. The occulting disk blocks the innermost region around the star, and beyond that disk, the usable field of view has a specific angular extent. Critically, the coronagraph also has a region of reduced sensitivity directly behind the occulting disk, a shadow zone where scattered light from the mask structure itself creates a blind spot in the data. If S1 occupies an orbit that is not flat relative to our line of sight, and unlike an inclined elliptical orbit rather than a circular one seen face-on, then its position in the sky, as seen from Earth, would change not just along a smooth curve, but in ways that could move it behind the mask's shadow zone or outside the useful coronagraphic field within a matter of months. Think of an actor mid-performance stepping behind the wings while the camera is still running. The performance has not ended. The actor has not ceased to exist. They have simply moved to a position the camera cannot reach. At exactly the moment the director chose to confirm they were there, the scene looks empty. The stage looks abandoned. But the absence is not the same as the disappearance. And then the archival data resurfaced a detail that changed everything. In 2019, 5 years before Webb's observation, 6 years before the field was even asking this question seriously, the Very Large Telescope in Chile conducted coronagraphic imaging of Alpha Centauri A in visible wavelengths as part of a survey program. In that dataset, partially buried in noise and never formally published as a detection, there was a faint signal logged in the reduction notes with the designation cone. Its position, its brightness at visible wavelengths, its angular separation from Alpha Centauri A, all of it was too marginal to report as a finding at the time. The threshold for a claim about Alpha Centauri had been set high after 2012. Cone did not clear that threshold. It was filed, archived, and left alone. In 2025, with S1's orbital mechanics being modeled across millions of simulated configurations. The team ran the coordinates and timestamp of Cone through the same dynamical framework. The result was not subtle. The position of Cone in 2019 and the position of S1 in August 2024 fit onto the same inclined elliptical orbit, two instruments, 5 years apart, one continuous path through the Alpha Centauri A system, threading through all the observations and all the gaps exactly as a planet with a tilted, elongated orbit would predict. Two different instruments, two observations separated by 5 years, the same point on the same orbit. Can you call that a coincidence? The answer lives inside millions of orbital simulations, and they pointed to a specific date that science now has no choice but to wait for. Any planet orbiting Alpha Centauri A does not simply orbit Alpha Centauri A. That is the gravitational reality of living inside a triple star system, and it changes everything about what stable orbital motion can look like. Alpha Centauri B, orbiting its companion across a distance that varies between 11 and 36 astronomical units over a 79.9-year cycle, exerts a continuous gravitational influence on anything bound to Alpha Centauri A. Not a catastrophic influence, not enough to tear a planet away immediately, but enough to nudge, tilt, and deform an orbit over millions of years in ways that have no analog in the cleaner, simpler architecture of a single star system. Like our own, Proxima Centauri, despite its enormous distance from the inner pair, adds a third gravitational voice to this conversation, fainter, slower, but present across timescales long enough to matter. The consequence is that planets in this system, if they exist, almost certainly do not follow the tidy circular orbits that Earth and Mars trace around the Sun. Gravitational perturbation over millions of years shapes orbits into elongated ellipses, tilts their planes relative to the star's equatorial disk, and drives slow oscillations in their orientation. A planet that began its life on a nearly circular, flat orbit could, over sufficient time, under the influence of two companion stars, evolve into something that looks wildly unlike anything in our solar system, inclined, eccentric, tracing a path that appears, from Earth's line of sight, to carry it through observational blind spots in ways that a simple equatorial orbit would never produce. This is the physical context inside which Wagner's team built their orbital analysis. The methodology they used is called a Monte Carlo simulation, a computational approach that does not seek a single correct answer, but instead maps the space of all possible answers by running millions of variations simultaneously. The team generated millions of candidate orbital configurations for S1, every combination of orbital period, eccentricity, inclination angle, orientation in three-dimensional space, an orbital phase that was mathematically compatible with the known gravitational constraints of the Alpha Centauri system. For each of those millions of orbits, they asked 4 questions in sequence. First, does this orbit place S1 at the angular position where it was detected in August 2024? If no, the orbit is eliminated. If yes, it survives to the next test. Second, does this same orbit, propagated backward in time to 2019, place an object at the angular position and approximate brightness where the Very Large Telescope recorded the cone signal again? Orbits that fail this constraint are removed from the pool. Third, is this orbit gravitationally stable over millions of years in a system containing Alpha Centauri A, Alpha Centauri B, and Proxima Centauri orbits that would be disrupted or ejected on timescales shorter than planetary formation. Epochs are discarded. A real planet must be able to have persisted long enough to exist. Fourth, does this orbit predict that S1 would move into the coronagraph's blind zone or outside the usable field of view between August 2024 and February 2025, explaining its absence in the confirmation observations? The orbits that survive all 4 filters converge on a specific family of solutions. They share 2 defining characteristics: high inclination relative to the plane of the sky as seen from Earth, and moderate eccentricity, not perfectly circular, not wildly elongated, but somewhere between the two. These are orbits shaped by the long influence of Alpha Centauri B's gravity, perturbed over millions of years away from the flat, circular geometry that simpler formation models would prefer. Picture a frisbee thrown not horizontally, but at a steep angle. 45 degrees, perhaps tilted sharply so that when you watch it from directly in front, sometimes you see the full disk clearly and sometimes you see only a thin sliver as it rotates through its trajectory. S1's inclined orbit behaves analogously when viewed through MIRI's coronagraph. At some orbital phases, S1 sits in a region of the sky that the coronagraph's usable field can access visible, detectable, recorded. At other phases, its inclined path carries it behind the occulting disk or into the shadow zone at the mask's edge, where scattered light from the coronagraph structure itself overwhelms any signal at that angular separation. From Webb's perspective, the planet does not disappear. It steps behind a door that the coronagraph built. 52%? That is the fraction of the surviving orbital solutions that predict S1 would move into exactly this inaccessible zone sometime between January and May 2025. The period covering both the February and the April follow-up observations that returned nothing. Not 52% probability that S1 is a planet. The number is more specific and more interesting than that 52% probability that, given S1 is a planet with an inclined orbit drawn from the family of solutions consistent with all observations, the disappearance in early 2025 is geometrically expected rather than anomalous. The disappearance is not evidence against S1's existence. Under the right orbital geometry, it is evidence for it. This inversion absence as confirmation rather than refutation is one of the more disorienting things orbital mechanics can produce, and it is exactly the kind of reasoning that separates a careful analysis from a credulous one. The team was not arguing that because S1 disappeared, it must be real. They were arguing that if S1 is real and has an inclined orbit, disappearance is precisely what the mathematics predicts, and the mathematics predicts it at a rate of more than half the viable orbital solutions. If absence is the evidence, and the evidence points forward rather than back then, we are learning to read the universe in reverse. And the model had already made a prophecy: one coordinate, one moment, one final chance to confirm or bury S1 forever. The best-fitting orbital models predict that S1 will reappear within the accessible field of MIRI's coronagraph in approximately August 2026, not a vague window of months or a range of years, a specific epoch, with a specific predicted position on the sky shifted to the northeast relative to where S1 appeared in August 2024, displaced by an amount consistent with nearly 2 years of orbital motion along an inclined elliptical path. Its predicted brightness in mid-infrared wavelengths, approximately 10,000 times fainter than Alpha Centauri A, comparable to the August 2024 detection. Assuming no dramatic change in the planet's thermal emission over the intervening period, the predicted position shift is not a minor technical detail. It is the critical test. Any sufficiently noisy dataset can produce a spurious point source once the lesson of 2012 made that viscerally clear. What it cannot easily do is produce a spurious point source twice, at 2 different positions separated by exactly the angular distance that 2 years of orbital motion on a specific inclined ellipse would predict. The combination of reappearance and positional offset is the signature that distinguishes a planet from noise. Noise does not follow orbital mechanics. Planets do. In the history of astronomy, The most dramatic demonstration of orbital mechanics as a predictive tool came in September 1846. Urbain Le Verrier, a French mathematician who had never looked through a telescope in his professional life, sent a letter to the Berlin Observatory containing a calculated position in the sky. He had derived this position purely from mathematics by analyzing anomalies in the orbit of Uranus that could not be explained by the known planets, and working backward through Newtonian mechanics to identify where an undiscovered planet would have to be to produce those anomalies. The night the observatory received his letter, astronomer Johann Galle pointed a telescope at Le Verrier's coordinates. Neptune was there, within 1 degree of the predicted position. The planet had been found by calculation before it was found by observation. August 2026 carries an echo of that moment, not an identical one. Le Verrier's prediction was built on years of precise orbital data from multiple observations of Uranus, while the S1 prediction rests on 2 detections separated by 5 years and millions of simulated orbital solutions. Le Verrier was working with certainty refined through decades of accumulated measurement. The S1 prediction is working with probability assembled from incomplete data and sophisticated modeling. The confidence level is not the same, but the structure of the test is exactly the same. A prediction, a coordinate, a date, and a telescope pointed at that coordinate on that date, waiting to see if the universe cooperates, as of June 2026. Right now, as this story is being told, the astronomical community is in a state of controlled anticipation. Multiple independent research groups have announced plans to conduct their own observations of Alpha Centauri A in the coming months, using both Webb and ground-based coronagraphic instruments to either confirm or refute S1's predicted reappearance. Webb itself has been allocated additional observing time for Alpha Centauri A in 2026, a resource that is intensely competed for and not granted without scientific justification. The fact that it was approved signals something about how seriously the field is taking this. For the first time in history, a planet has an appointment with humanity. August 2026, a coordinate in the sky that the math says S1 will occupy. A window of weeks during which the best telescope ever built will look at exactly that position and either see a faint point of mid-infrared light or see nothing at all. This is science working the way it is supposed to work, not a claim without a test, not a detection without a falsifiable prediction, a specific, quantitative, observable consequence of a hypothesis, waiting to be checked by instruments that do not care what the answer is. The universe will not adjust its behavior to match anyone's preferred narrative. Either S1 is there in August 2026 at the predicted coordinates, at roughly the predicted brightness, or the hypothesis fails. The orbital family is ruled out, and the field starts over with a harder question. There is something genuinely rare about this moment. Most scientific questions at the frontier unfold over decades, accumulating evidence slowly, building toward conclusions that arrive not as sudden revelations, but as gradual shifts in consensus. The S1 question has a deadline, a hard one, the kind of test that resolves ambiguity rather than accumulating more of it. 2 months from now, you are reading this at the moment before the answer exists. That is not a common place to stand in science. The first time in history, a planet made an appointment with humanity, and nobody knows if it will keep it. But even if S1 reappears and is confirmed, we will still have to face a harder truth that is only what we can see, not what is actually there. Try this thought experiment. Place a civilization at Alpha Centauri, intelligent, curious, technologically advanced to exactly the level humanity has reached in 2024. Give them a telescope equivalent to James Webb, point it at the Sun, 4.3 light-years away, and ask them what they find orbiting it. The Sun from that distance would be a brilliant point of light apparent magnitude roughly 0.5, comparable to how we see Alpha Centauri from Earth. Their coronagraph would block the sun's direct glare. Their detectors would settle and begin reading the faint thermal signatures of anything orbiting nearby. They would process the data, strip the noise, apply the same pipeline techniques Wagner's team used, and then they would look at what remained. Jupiter would be there. Almost certainly. Its mass is 318 times that of Earth, the largest planet in our system, by a factor of more than 2 compared to everything else combined. More importantly, Jupiter radiates more energy than it receives from the Sun, generating internal heat from the slow gravitational contraction of its enormous bulk. That internal luminosity, modest by stellar standards, but significant by planetary ones, pushes Jupiter's mid-infrared emission high enough to be detectable at 4.3 light-years with a Webb equivalent instrument. Jupiter sits 5.2 astronomical units from the Sun, far enough from the star that a coronagraph positioned on the Sun would leave Jupiter outside the blocked inner region, sitting in the accessible field where faint signals can be measured. The hypothetical Alpha Centauri astronomer would see it. Saturn is a harder case, but plausible. It is smaller than Jupiter, and its internal heat output is lower. But it is still a gas giant nearly 100 times the mass of Earth, still warm, still radiating. At 9.5 astronomical units from the Sun, it sits comfortably in the coronagraphic field. Whether a Webb equivalent instrument at 4.3 light-years could pull Saturn's signal above the noise threshold is uncertain. It sits right at the edge of feasibility. Depending on processing assumptions, perhaps visible, perhaps not. A marginal detection at best. Earth completely invisible. Consider the numbers plainly. Earth's mass is 1/318th of Jupiter's. Earth generates almost no internal heat. The small amount from radioactive decay in its mantle is negligible in mid-infrared terms compared to a gas giant's convective luminosity. Earth orbits the Sun at 1 astronomical unit, placing it deep inside the coronagraph's inner exclusion zone where scattered stellar light dominates the noise floor absolutely. And even if the geometry were different, even if Earth sat at a more favorable orbital distance, its thermal emission at mid-infrared wavelengths from 4.3 light-years would fall below the detection threshold of any coronagraphic instrument that currently exists or is currently planned. Mars invisible, Venus invisible, Mercury invisible, the entire inner solar system, every rocky world, every place where complex chemistry exists at temperatures compatible with liquid water would be absent from the data. The Alpha Centauri astronomer would look at our solar system and see 2 gas giants, possibly, and a star, nothing else. No indication that the third rock from the Sun harbors every form of life that has ever been confirmed to exist in the observable universe. Think about what it looks like to photograph a city from an altitude of 40,000 feet at night. You see the major commercial zones, the airport, the downtown core, the large shopping complexes. Their lights bright enough to punch through the distance and register clearly. You do not see the residential neighborhoods, the small houses on quiet streets where the actual population lives, where children sleep and food is cooked and lives unfold. Those neighborhoods are dark at 40,000 feet. The light from a single porch lamp does not reach you. You would map that city as a handful of bright commercial nodes surrounded by empty darkness, and your map would be profoundly, systematically wrong about where most people are. Earth is the quiet residential neighborhood. The biosphere, every forest, every ocean, every living cell on the planet generates no signal visible at 4.3 light-years with 2024 technology. The only confirmed repository of life in the known universe is, from the perspective of the nearest star, completely dark. Humanity built a $3 billion telescope capable of seeing light from more than 13 billion years ago. from galaxies that formed before the Milky Way existed, and that same telescope, repositioned to Alpha Centauri and pointed back at home, would miss the planet where it was assembled? That is not a criticism of the telescope. It is a precise statement about the scale of the detection problem. If we are invisible in our own best instrument's data, are we searching for life out there? Or are we searching for the shadow of ourselves? This is not merely a technical problem. It is an epistemological one, and it may be quietly undermining the entire foundation of how we count worlds in the Milky Way. As of 2025, the NASA Exoplanet Archive contained more than 5,700 confirmed planets beyond our solar system. That number's remarkable. It represents decades of work by thousands of astronomers, millions of hours of telescope time, and computational pipelines processing petabytes of photometric and spectroscopic data. The catalog is real, the planets are real, and the science that produced them is among the most consequential in modern astronomy. It is also, structurally, a deeply biased document, not through error or negligence, but through the inescapable physics of how planets are found. The dominant detection method in that catalog is the transit technique, measuring the fractional dimming of a star's light when a planet passes in front of it along our line of sight. Kepler, the space telescope that ran from 2009 to 2018, found roughly 2,700 confirmed planets using this method alone. TESS, its successor, has added thousands more. The transit method is extraordinarily powerful, but it selects strongly for specific kinds of planets in specific kinds of orbits. A planet only transits its star if the orbital plane happens to be aligned edge-on, relative to Earth's line of sight. That alignment is geometrically rare, especially for planets in wide orbits. More importantly, the transit signal. The fractional dimming scales with the planet's size relative to its star. A Jupiter-sized planet blocking a sun-like star produces a dimming of roughly 1%. Earth blocking the same star produces a dimming of roughly 84 parts per million, a signal so small that detecting it consistently requires years of continuous, high-precision photometry. Rocky Earth-sized planets at habitable zone distances around sun-like stars are at the absolute edge of what Kepler could detect, and most of what it found at that boundary remains statistically ambiguous. Direct imaging, the method Webb is applying to Alpha Centauri, selects in exactly the opposite direction. It preferentially detects planets that are large, warm, and far from their host stars. Gas giants at wide orbital separations radiate enough internal heat to be visible directly. Small rocky planets close to their stars are lost in the stellar glare. The combined effect of these selection biases is a catalog heavily weighted toward planets that are either large or tidally locked in extremely close orbits, or both. It is not a representative sample of what the Milky Way actually contains. It is a catalog of what is detectable by the methods we have built, and those methods have structured blind spots that correspond precisely to the category of planet most likely to support complex life as we understand it: rocky, moderate-sized, orbiting at habitable zone distances around stable stars. The scale of what might be missing is difficult to state without making assumptions, but conservative estimates suggest that the number of rocky planets in habitable zones across the Milky Way could be in the billions. Not detected, not confirmed. Simply below the horizon of every instrument we have operated so far. Alpha Centauri, the nearest system, the most studied, the one we cannot analyze clearly, even with Webb, is the sharpest illustration of that gap. If we cannot determine whether a Saturn-mass planet exists at 2 astronomical units from the nearest sun-like star, the confidence with which we should make statistical claims about Earth-sized planets around stars tens of light-years away deserves serious re-examination. Frank Drake formulated his famous equation in 1961 as a framework for estimating the number of technologically communicating civilizations in the Milky Way. One of its key terms is the fraction of planets that develop life, which in turn depends on knowing how many planets with suitable conditions exist. Drake's equation is not a calculation, so much as a structured acknowledgement of what we do not know, organized into terms that direct future inquiry. But its application requires plugging in numbers, and the numbers we plug into the planetary habitability terms come directly from our detection catalogs. If those catalogs are systematically biased, not randomly wrong, but wrong in a specific direction that undercounts the very planets most relevant to the question of life, then every estimate of civilizational frequency that rests on them inherits that bias. The terrifying possibility is not that the universe is empty. It is that we have been counting the wrong things and calling the result an answer. The void of the exoplanet catalog is not a void in reality. It is a void in sensitivity. Our instruments have mapped the loudest signals and labeled the silence around them as emptiness. What Alpha Centauri teaches with brutal specificity, from a distance of only 4.3 light-years, is that the silence is not absence. It is the sound of things too small and too faint to hear with the ears we have built. If our tools can only see the large, then the empty universe might just be a very normal incomplete catalog, wearing the costume of a philosophical conclusion. And this is the moment Alpha Centauri stops being the story of one star system and becomes the mirror that reflects the gaps in the entire theoretical framework of modern astrophysics. Every planet in existence, including the one you are standing on, began as dust, the nebular model of planet formation, which has been the dominant framework in planetary science since the mid-20th century and has accumulated overwhelming supporting evidence across thousands of observed protoplanetary systems, describes the process in broad strokes that are now well enough established to be taught in introductory astronomy courses. A cloud of gas and dust collapses under gravity. The center ignites into a star. What remains orbits as a flattened disk, the protoplanetary disk, and within that disk, particles collide, stick together, grow through accretion from grains to pebbles, to planetesimals to planets, over timescales of millions to tens of millions of years. The process is slow, statistical, and shaped entirely by the gravitational environment surrounding it. In a single star system, like our own, that environment is relatively clean. One dominant gravitational source at the center, the disk orbiting it symmetrically, perturbations arriving mainly from the growing planets themselves. The resulting architecture tends toward orderly, roughly circular orbits, orbital planes that cluster near the star's equatorial plane, a progression from rocky inner planets to gas giants in the outer regions where temperatures were cold enough for ice to condense during formation and give the growing giants their enormous mass budgets. Binary star systems break this picture in a specific and well-understood way, or at least a way that was considered well understood before August 2024. The second star, orbiting the primary at some distance, imposes a time-varying gravitational perturbation on the disk. Simulations going back decades consistently show that this perturbation truncates the disk. Material beyond a certain radius cannot maintain stable circular orbits because the companion star's tidal forces stir up orbital velocities, increase collision speeds from gentle accretion to violent fragmentation, and over time, clear the disk of material that would otherwise build planets. The threshold for disk truncation in a binary system is typically estimated at roughly 1/3 to 1/2 of the companion star's orbital separation. For Alpha Centauri A and B, whose separation varies between 11 and 36 astronomical units across their 79.9-year orbit, this implies that the disk around Alpha Centauri A was likely truncated at a few astronomical units, perhaps 2 to 4 astronomical units at most, depending on disk properties and orbital parameters at the time of formation. This is precisely where the theory runs into S1. If S1 is confirmed as a planet with a highly inclined, moderately eccentric orbit at approximately 2 astronomical units from Alpha Centauri A, it sits exactly at the inner edge of the zone where theory predicts disk truncation becomes severe, not safely inside the stable region, not comfortably beyond the binary's reach. Right at the boundary on an orbit that the gravitational simulations of binary disk dynamics say should not have permitted stable planet formation in the first place. And it is not on a flat, circular orbit. It is inclined. That inclination itself is deeply problematic for the nebular model, which forms planets from a disk that is, by construction, nearly planar. A planet on a highly inclined orbit relative to its star's equatorial plane cannot have formed in a flat disk and stayed there. Something moved it. The question of what moved it, or whether it formed where it is at all, generates 3 distinct explanatory scenarios, none of which is comfortable. The first S1 formed in place, in the disk around Alpha Centauri A, and survived through some mechanism that the current theoretical models do not adequately capture. Perhaps the disk was denser than typical models assume, allowing accretion to complete before tidal disruption could clear the material. Perhaps magnetic fields in the disk played a role that has been underweighted in the simulations. Perhaps there are resonance effects in the 3-body gravitational environment that can stabilize planet-forming material at this location in ways that 2-body disk models miss entirely. This scenario does not require invoking exotic physics. It requires acknowledging that the models are incomplete, which is itself a significant concession from a field that has spent decades refining those models against observations of protoplanetary disks around other stars. The second scenario, S1, formed on a different, more stable orbit closer to Alpha Centauri A, well within the protected inner region, and was subsequently perturbed into its current inclined, eccentric configuration by a gravitational interaction. The most likely agent of such an interaction would be Alpha Centauri B, which during past epochs of its orbit may have passed at separations closer to 11 astronomical units from Alpha Centauri A, delivering gravitational impulses that could have excited the inclination and eccentricity of a planet initially on a quiet inner orbit. This is called secular perturbation, the slow, cumulative twisting of an orbit by a distant companion over millions of years. It is a known mechanism. It operates in our own solar system to a small degree, but producing the level of inclination implied by S1's orbital solutions from an initially flat, stable orbit requires a perturbation history that pushes the edges of what the Alpha Centauri binaries' past configurations can plausibly deliver. The third S1 was not formed around Alpha Centauri A at all. In the dense stellar environment of the early solar neighborhood, when stars were forming closer together, moving through gas-rich clusters, gravitational encounters between young stellar systems occasionally resulted in planetary objects being scattered out of one system and captured by another. A free-floating planet, or a planet ejected from a forming system nearby, could in principle have been captured into a bound orbit around Alpha Centauri A if the encounter geometry was favorable and the triple star system's gravitational cross-section was large enough to trap it. Capture is rare. In most models of the current Milky Way, it is vanishingly rare, but not impossible, particularly in the early epoch of the galaxy's stellar history, when stellar densities were higher and close encounters more frequent. None of these 3 scenarios is obviously correct. None can be ruled out with current data. All 3 require either rewriting a piece of established planetary formation theory, invoking a specific and somewhat improbable dynamical history, or accepting a mechanism so rare that invoking it as an explanation feels epistemologically uncomfortable. It is like finding a skyscraper standing undamaged in the middle of a magnitude 8 earthquake zone, with no foundation design on record that could have supported it. You do not deny the building is standing. You can see it clearly. But you are forced to rewrite the building codes because the building's existence proves that something the codes said was impossible is not. You are probably thinking S, one has not been confirmed yet. The theory might still be intact. Perhaps the data will resolve cleanly in August 2026, or fail to resolve, and the theoretical framework will emerge untouched. That is a fair thought. But here is the point we do not know, and the not knowing. In this specific system, at this specific distance, after this specific investment of observational effort, is itself the problem. The theory should be testable at the nearest star. The fact that it remains genuinely uncertain, not through lack of effort, but through the fundamental difficulty of observation at 4.3 light-years, means the theory's predictive power at its closest possible test case is not what anyone assumed it was. But the collapse of planet formation theory is only the first floor. The second floor reaches up into everything we thought we knew about the entire Milky Way. Roughly 50% of all stars in the Milky Way exist in binary or higher order multiple systems. That fraction varies by stellar mass. More massive stars have a higher multiplicity rate. Lower mass red dwarfs, somewhat lower, but across the full stellar population of the galaxy, the majority of stars share their gravitational environment with at least one companion. Single stars like the Sun are, statistically speaking, the less common configuration rather than the norm. This matters enormously for the question of how many habitable planets the Milky Way contains. And it matters in a way that has been systematically underweighted in every statistical estimate produced over the past 3 decades. The occurrence rate models that astronomers use to estimate how many planets of a given type orbit, how many stars of a given type, are built primarily on data from 2 missions, Kepler and TESS. Both of those missions detected planets predominantly around single stars. The reason is partly observational. Binary stars complicate the photometric analysis needed for transit detection, and many binary systems were excluded from Kepler's primary target lists to reduce that complexity. The result is a catalog of planetary occurrence rates that is heavily calibrated to single-star environments and extrapolated to binary systems under the assumption that the underlying physics is similar enough to make the extrapolation valid. That assumption has always been questioned at the theoretical level. Binary disk dynamics differ from single-star disk dynamics in ways that should suppress planet formation at certain orbital ranges and potentially enhance it at others. But the observational data to test those theoretical predictions has been sparse, precisely because binary systems are harder to analyze and were underrepresented in the major survey samples. Alpha Centauri is the point where that theoretical gap becomes an empirical crisis. If S1 exists on an orbit that formation theory says should not be stable in the nearest, best studied, most data-rich binary system available to astronomy, then the extrapolation of single-star occurrence rates to binary environments is not just uncertain, it is built on a foundation that the nearest available test case cannot support. The consequences ripple outward. Current estimates of the number of potentially habitable planets in the Milky Way range from hundreds of millions to tens of billions, depending on the assumptions made about what constitutes habitability and what fraction of stellar systems host Earth-like worlds. Those estimates are stated with varying levels of confidence, but they share a common dependency on the occurrence rate models derived from Kepler and TESS. If binary systems can produce planet populations that differ fundamentally from those models more eccentric, more inclined, existing at orbital distances and geometries that single star formation theory predicts should be empty, then the total count of potentially habitable environments in the galaxy is genuinely unknown, not uncertain within a factor of a few. Unknown in a more basic sense, the category. Boundaries themselves may be wrong. The number could be higher than current estimates suggest. If binary systems harbor planets on a wider variety of orbits than theory predicts, and if some of those orbits carry planets through regions that are intermittently habitable, or if gas giants on inclined orbits host moons in protected thermal environments, then the inventory of places where life might emerge is larger than the catalog implies. Or the number could be lower if the perturbation history of binary systems tends to destabilize planetary orbits on long timescales, ejecting planets that initially formed in favorable positions into cold interstellar space before life has time to take hold. The data at present cannot distinguish between these possibilities. This feeds directly into the Fermi paradox, the question of why, given the apparent abundance of potentially habitable environments in the Milky Way. We have not detected any signal of technological civilizations elsewhere. If the number of genuinely habitable planets is larger than current estimates, because binary systems contribute substantially to the inventory in ways we have not modeled, the paradox deepens. The universe would contain more potential addresses for civilization than we thought, and the silence becomes even harder to explain. If the number is smaller because binary dynamics are more destructive to planetary stability over long timescales, the paradox partially resolves. There are simply fewer places where life had the time and stability to reach technological complexity. Alpha Centauri sits at the center of both possibilities simultaneously, unable to resolve the paradox, but perfectly positioned to destabilize any answer that claimed to be resolving it. Astronomy has produced many estimates of how many civilizations might exist in the Milky Way. Every single one of those estimates now shares one characteristic in common. They were all calculated without a reliable understanding of how planets form and survive in the stellar environment that covers half the galaxy. The nearest star gave us that problem as a gift. If even Alpha Centauri, the most studied stellar system outside our own, the subject of more dedicated observational effort than any other external target in the history of the field, still hides structures that our best theories failed to predict, then how much confidence should we place in the numbers we attach to stars we can barely resolve at all? And this is the final blow, not from the data, not from the models, but from the philosophy of science itself. 4.3 light years. That is the physical distance, the smallest gap between our solar system and any other star. In the vocabulary of cosmic scale, it is practically nothing. Light covers it in 4 years and a few months, a number so often repeated in discussions of Alpha Centauri that it has acquired the comfortable familiarity of a well-worn fact, something to anchor the imagination when the rest of astronomy becomes too abstract to hold. But there is another kind of distance, not measured in light years, not reducible to a number, not closable by building a larger telescope or running a faster simulation. The epistemological distance, the gap between physical proximity and actual understanding, and for Alpha Centauri, that distance remains, in a meaningful sense, effectively infinite. We do not know if a planet orbits Alpha Centauri A. We do not know the system's full planetary architecture. We cannot confirm whether the habitable zone around either sun-like star contains anything at all, rocky or gaseous, that has survived the gravitational complexity of a three-body system over billions of years. After decades of observation, after the false alarm of 2012, after the extraordinary technical achievement of the blind offset maneuver in August 2024, after S1 appeared and then vanished and then pointed toward August 2026 as a reckoning, the honest summary of humanity's knowledge of the nearest star system. Is this? We are not sure. We have compelling hints. We have a testable prediction sitting 2 months in the future. We do not have knowledge in any rigorous sense of the word. That gap, physical nearness and epistemic distance coexisting simultaneously, breaks a deeply embedded assumption about how science is supposed to work. The assumption is intuitive and almost never articulated explicitly, that closing physical distance produces understanding. Get closer to the object and you learn more about it. Build instruments that simulate proximity and the knowledge follows. It is the logic that sends rovers to Mars. probes to Pluto, and ambitious proposals like breakthrough star shot toward Alpha Centauri itself. Proximity in this framework is the currency of knowledge. Alpha Centauri is the proof that the currency can be counterfeit. The reason cuts to the core of what observation actually is. When an astronomer looks at Alpha Centauri, they are not seeing it. They are receiving light electromagnetic radiation that left the system 4.3 years ago, carrying information encoded in its wavelengths about the physical state of that system at the moment of emission. That light then passes through 1 trillion kilometers of interstellar space before entering an instrument designed by engineers operating under constraints of mass, power, thermal stability, and orbital mechanics. The instrument converts the photons into electrical signals. Those signals are processed by software built on algorithms that embed assumptions about what kinds of noise exist and how to remove them. The clean data is then interpreted through theoretical frameworks, planet formation models, orbital mechanics, stellar atmosphere physics, each of which has a domain of applicability that may or may not include the conditions at Alpha Centauri. At every single stage, between the physical reality of the system and the conclusion written in a journal paper, there is a filter. Each filter can obscure, each can distort, each can, under the wrong conditions, generate a signal that was never there or erase one that was. Alpha Centauri is the clearest demonstration of all those filters operating simultaneously. The brightness filter too much light, requiring a blindfold maneuver. The noise filter, the binary's gravitational complexity, contaminating every spectroscopic measurement. The data processing filter, the 2012 false detection, where the subtraction algorithm sculpted a phantom from residual binary noise. The coronagraphic geometry filter, a planet potentially hidden behind the mask's shadow zone during follow-up observations. Every layer of the detection pipeline in this system has revealed its capacity to both reveal and deceive. Understanding Alpha Centauri requires not just better instruments, but a more rigorous accounting of every assumption embedded in the process of using them. What the field needs not merely for Alpha Centauri, but for the broader project of finding Earth-like worlds around Sun-like stars, is technology that differs in principle, not just in scale. Space interferometry represents that different principle, an interferometric array of telescopes in space, separated by distances of hundreds of thousands of kilometers and operating in concert, would synthesize an effective aperture large enough to directly resolve the disk of a nearby star and detect the reflected light or thermal emission of a rocky planet orbiting within its habitable zone, not by blocking the star's light with a coronagraph and hoping the residual is manageable by spatially resolving the star and planet as separate objects. The way a radio telescope array resolves distant galaxies that optical telescopes see only as points. NASA's Habitable Worlds Observatory, currently in the advanced study and advocacy phase, with formal mission concept development ongoing, represents the next proposed step in that direction. Its primary scientific objective is the direct imaging of rocky planets in the habitable zones of nearby sun-like stars. Using a large space telescope equipped with a sophisticated starshade or internal coronagraph optimized for visible and ultraviolet wavelengths, where reflected starlight from rocky planets carries the most information about atmospheric composition. If funded and built on the timescale currently discussed launch sometime in the late 2030s or early 2040s, its first and most important target will be Alpha Centauri A and B. Not because the system is culturally significant, though it is, because it is the nearest, the brightest, and the one place where the detection of an Earth-sized planet in a habitable zone, if one exists, would be within the instrument's reach. The funding is uncertain. The schedule is uncertain. The political and budgetary environment of large NASA flagship missions is not a domain where certainty has historically flourished, but the scientific case is beyond dispute. We have sent messages into space. We have built telescopes and pointed them at stars for a century. We have planned interstellar missions to a destination we cannot fully characterize. And after all of that, the system 4.3 light-years away has spent the last decade demonstrating, with patient precision, how much we do not know about it. If that does not make you want to understand what we are missing at the places much farther away, the thousands of stars where we have even less data, even less observational resolution, even more assumptions carrying even more weight, then no number in this story will? Alpha Centauri is not the answer. It is the question stated in light, gravity, and silence, a question that technology has not yet decoded, but one powerful enough to redefine what we mean by understanding. On any clear night in the southern hemisphere, you can step outside, look up, and see it with no instrument at all. A bright point of light, steady and warm in the constellation Centaurus, no telescope needed, no special knowledge required, just eyes and sky. That point of light contains everything described across these 15 sections. The three-star system we misread for decades. The binary pair too bright for our best instrument to face directly. The ghost signal that appeared in processed data and then stepped behind a curtain. The orbital mechanics pointing like a compass toward August 2026. All of it is packed into a pinpoint of photons that any human being anywhere in the southern hemisphere has always been able to see with their own eyes, and which science, for all its power, still cannot fully read. S1 may be a planet. The data is genuinely suggestive, and the prediction is falsifiable. August 2026 may produce a confirmation that rewrites every textbook chapter on binary star planetary systems and reignites the question of whether the nearest sun-like stars host worlds capable of supporting something. Or the observation may return empty, and the field will return to the problem with harder questions and more constrained parameters, which is also how science advances. Neither outcome closes the story. Certainty in science is not the default state. It is the rare achievement that arrives after many acknowledged errors, and it is never permanent, only provisional, held until the next observation demands revision. Standing at the edge of understanding is not a failure. It is the only position from which progress is possible. Every fact we now hold confidently about the cosmos was once the unresolved question at the frontier of someone's career, the anomaly in someone's data, the signal that appeared once and then needed explaining. Everything we know about the universe was once something we did not know, and everything we do not know today is the shape that tomorrow's science will take. Alpha Centauri 4.3 light-years, 3 stars, 1 ghost of a planet, and more open questions than any system this close should be permitted to contain is not a failure of astronomy. It is proof that the universe is still large enough to surprise us. And that, in the end, is the best news we have.